Okay, so welcome back to particle physics and standard model. This is lecture 7, and so last time we explored the concept of charge conjugation, and in particular we talked about it as an intrinsic quantum number, and then we found that there were only certain states that could be the eigenstates of charge conjugation, and those turned out to be, in a loose sense, particles that are their own antiparticles, right. And so we saw the photon and the pion and so on were C eigenstates, and we worked out the eigenvalues of certain states and some particle physics implications, some particle physics process implications of having C as a good quantum number, right. Now let us press further and see how to combine some of these discrete symmetries. Okay. So we saw that we saw what happened to some processes under parity. We also know what happens to processes under charge conjugation, right. Let us see what happens under the combination of them. So in particular, let us explore the concept of CP, the combination of charge conjugation and parity. Okay. So let us take this example that we saw a couple of lectures ago of the pi 0 decaying to a mu plus and a mu1 neutrino, right. Now I am going to remind you that it was from this process that it was discovered that the neutrino, in this case the mu1 neutrino, is a left handed state. How? Because you could measure the helicity of the mu plus, and then by conservation of spin and conservation of momentum, the helicity that you measure of the mu plus turned out to be the helicity of the neutrino, right. So I encourage you to go back 2 or 3 lectures back to see how this was derived. So what this means is that just going to summarize this here, a left handed neutrino, left handed mu plus was got, and at the same time you got a left handed neutrino, right. Okay. Now I am going to apply charge conjugation on this whole thing. So I am going to write ditto. Ditto just means this whole process. If I apply charge conjugation, right, I get, what do I get? I just flip the pion's charge, and then I just flip the muon charge, the anti-muon becomes the muon now, and then I take the neutrino to be the anti-neutrino, correct. But notice that all I have done is a hypothetical charge conjugation to the entire process, right. I have not touched the parity here. So in this hypothetical transformation, all that has happened is that the muon has flipped charge. That means here I still have mu minus as left handed, and the anti-neutrino also as left handed. So we know in nature this is not true, but just bear with me, okay. Just this is a thought experiment where I apply charge conjugation, I get a left handed muon and a left handed anti neutrino, right. But we can save the day now. Well, we can always save the day by putting in one more charge conjugation and then you go back to the first equation, but that is not what I am going to do. I am going to apply parity to this entire process. Then what happens? Then I still have the pion, obviously parity does not change any of these quantum states. So I am still going to write down the same process, but the real change has happened here now, right. So now I have just flipped the muon to a right handed state, just flipped the helicity by applying parity, and I have flipped the anti-neutrino to a right handed state, got it. So by doing 2 thought experiments, first flipping the charge conjugation and then flipping the parity, what I have done is in the end I get a process that is a right handed, that is a pion going to a right handed anti-neutrino and a right handed muon. Now this is exactly what you would expect in real life also, the final thing, right, the final process. Of course if I have a pion, I am going to get a right handed a pion with a minus charge, I am going to get a right handed anti-neutrino, and a right handed muon, right. In other words, by doing 2 successive thought experiments, we got something back that is correct in reality. Agreed? So, when parity was discovered, right, sorry, when it was discovered that the weak interactions violated parity in a maximal way, I told you that people were very disturbed psychologically, although they gave a Nobel Prize very quickly. People were very, very disturbed that the world looks different in a mirror, completely different in a mirror. But then there was a solace back then that at least if you apply charge conjugation, that is, you go to the mirror image and then in the mirror image you change all the particles to their antiparticles, then again the world there looks the same. So, you lost a mirror image, but at least this combination gave you back the world. So, it was this combination, right, of CP was at least this was thought to be the fundamental symmetry, okay, and it was a very it was a very cherished principle that at least CP is the underlying symmetry. Let me write it down because it is important. Underlying symmetry of weak interactions, not P but CP. Okay. Let me ask a quick question here. Is C an underlying symmetry of the weak interactions? We saw P is not. What about C? C also is not. How do we know that? Because last time we saw that if I apply C to the neutrino, which is left handed, I get back a left handed anti-neutrino which is not there, right. So, and neutrino is again, neutrinos you do not see anywhere other than in weak interactions, right. Neutrino is the face of the weak interactions. So, C is not a good symmetry for weak interactions either, okay. So, neither P nor C, but at least CP, we got some symmetry back. There is symmetry in the world. This is what people were happy about, except, okay, it was found that even CP is violated, okay. This I think came as a this probably came as an even bigger shock actually. So, this is kind of even more fundamentally disturbing than just BP violation. That is, there is no real symmetry to talk about in nature as far as weak interactions go. There do seem to be symmetries in electromagnetism, but why does the weak interaction behave like this? Okay. So, when this was discovered and that even CP had to be given up, that was a very profound sacrifice. The world really is not as symmetric as we think at a fundamental level. Okay. Not only that, this has a spooky consequence, okay, and that is what we are going to talk about for the next 5 or 10 minutes. The spooky consequence is that we at least think that the world is at least Lorentz invariant, right, that under Lorentz boosts, if you go to a different inertial frame, laws of physics do not change, all those cherished principles of relativity that Einstein gave us, at least for flat space, right. At least there should be Lorentz invariance, and the way Lorentz invariance shows itself up in quantum field theory and particle physics is through, this is a very neat thing, it is through something called the CPT theorem, okay. I am just going to write that is equivalent to Lorentz invariance in the context of quantum field theories. Okay. So, what is the CPT theorem? Simply that if for any process in quantum field theories you apply C, charge conjugation, P, parity, and then T, which is time reversal, you flip the sign of time. Okay. If you apply these 3 in sequence, then this at least is preserved, okay. Because if you want Lorentz invariance, you need to have CPT as a combination to be preserved at least, okay. So, how do we know that? Let me give you a quick and dirty proof of the CPT theorem, okay. Okay, so here is the proof of the CPT theorem, okay. This is not the most rigorous proof, but it gives you a very good idea, it gives you a very good physical idea of what is going on. Okay. So, I am going to consider one dimension of space and draw the space time diagram that you are familiar with from relativity, special relativity, right. Okay. Now, there is something special about quantum field theories, which is that you can in many cases you can just take Euclidean space and treat it as Minkowski space. Okay. So, in relativity for Lorentz transformations we are always in Minkowski space, right, but in quantum field theories, that is the key here, I can do something called a Wick rotation where I can make time an imaginary coordinate, so that the metric which is a dt square minus dx square now becomes minus dt squared minus dx squared. So, it now looks like Euclidean space, right, the interval is now Euclidean. What that means is that on the space time diagram, right, if I want to do a Lorentz transformation, that is equivalent, a Lorentz transformation, I am going to write it in this way, is equivalent to a rotation in Euclidean space, right. So, if I want to I can always rotate these coordinates such that I end up with coordinates that look like this now. Okay. X has flipped, t has flipped, but all I have done is basically a rotation. Okay. Okay, that is my Lorentz transformation. Now, let us apply the CP, let us apply CP and T here. Okay. What happens if I apply P? Under P, I have flipped my X but not the T, correct. What happens under time reversal? Under time reversal, I have now flipped time but not X. So, what has happened now? I have recovered what I started with, right, before I did the Lorentz transformation by applying P and T. Okay. So, where is C here? I need both, I need all three, right. So, here is where Feynman's statement comes in. What did Feynman say? Remember, he said once, which we will see to be true when we deal with the quantum field theory aspects. Okay, we will see some of it is true actually, that a particle moving forward in time is equivalent to an antiparticle moving backward in time. Okay. If you have not heard of this statement, go look it up, it is a very interesting thing. Okay. So, now we flipped time, right. So, if we now apply charge conjugation, it is the equivalent of an antiparticle now moving in this backwards time. So, we have recovered what we began with, a particle moving forward in time. Okay. In this sense, CPT is equivalent to invariance under Lorentz transformations. Okay, very good. So, what is the spooky consequence now? Having learnt this, it means that since CPT is preserved, if CP is violated, right, it also means that T is violated, and that is spooky. Why? Because at least we think that the laws of physics should not change if we reverse the universe, right. If we run the video backwards on all phenomena, at least that should not change actually, right. T is time reversal, but it turns out that the reversed universe, okay, the reverse video of the universe actually would be different. The laws there, the interactions and everything that we put in there would be different in that universe. Okay. So, not only does the world look different in a mirror, not only does the world look different when you flip all charges and all the particles and antiparticles with each other, it also looks different if you look at it in backwards in time. Okay. So what does this mean in somewhat philosophical terms? It means that there is an arrow of time even at a fundamental level. What do I mean by that? All of this we are doing at some microscopic quantum level, right? We are using quantum field theory, quantum mechanics and so on. So at a fundamental level, there is a direction in which all things flow. There is a direction of time. We already know, obviously, from lived experience as well as from physics arguments, that there is a direction of time. There is an arrow of time. You would have seen it in Stephen Hawking's books, for instance, right? There is an arrow of time for the macroscopic universe, correct? And where does that arrow come from? At the macroscopic level, it comes from entropy. This is what we learnt, right, from Hawking and everybody else, that because entropy always increases for a closed system, you can turn this around and say that the arrow of time comes because entropy is increasing, that the time seems to be increasing, time seems to be flowing in a single direction because of entropy increase. You can just turn it around and say that. That is how the increase in entropy is what we perceive as time itself, right? So you might have heard of this argument. If not, go think about it more, go read about it more. It's a very interesting argument. So that that itself is a mystery, but for quantum physicists we can sort of live with that arrow of time, okay? But we are now finding that not only at a macroscopic level, even at the quantum microscopic level, there is another arrow of time coming from CPT theorem and CP violation in the weak interactions, right? Now, are these two arrows of time related? These two arrows of time, have they anything to do with each other? The answer is nobody knows. People are trying very hard to understand this. Okay, so it's a very deep mystery, and we're not going to talk about this further here. Okay, I encourage you to go and think about it. Okay, now having said all this, having talked about what the physical implications are of CEP, CP, CPT and all that, there is one thing one should not forget. We will encounter this further in the course, which is that CP violation, I am going to write CPV for CP violation, okay. CP violation is a profound thing, is a profoundly disturbing thing, but not really mysterious for weak interactions, because it would follow from the fact that there are 3 generations of matter. We saw this, right, in the very first lecture, like you had electrons, muons and tauons and their neutrino equivalents, you had up, charm and top, you had down, bottom and strange and so on, right. And then even in the QUDLE prescription, we separated everything into 3 nearly identical copies, correct. We are going to see how just the fact that there are 3 generations of matter, okay, not 2. If you had 2, then you wouldn't have CP violation in the weak sector. But having 3 automatically introduces something called a CP violating phase into the entire structure, and that is the source of all CP violation in weak interactions. Okay? Anything more than 2 is you are going to get CP violation in the weak interactions. Okay, but what is a mystery is not CP violation in the weak interactions, it has to do with CP violation in the strong interactions. Okay? Now, this is not particularly obvious. If I were to ask you, does the strong interactions satisfy CEP, right? That is not very obvious actually. You have to learn more about strong Lagrangians and so on, okay, non-abelian Lagrangians and so on. But let me give you a Fermi calculation or back of the envelope calculation for why we think that the strong interactions have a problem. Okay. Let me introduce that problem to you. This is called the strong CP problem. Okay. The problem is not that we observe CP violation. The problem is that we do not observe CP violation in the strong interactions. Okay. You expect there to be a lot of CP violation in strong interactions. Okay. So let me tell you why we think that. Okay. For that I am going to tell you something that you have to take for granted for now. In the next lecture we are going to see why this is true. To measure CP in a system, you measure the electric dipole moment of that state. Okay. Just take this from me for now. In the next lecture we are going to see why this is the case. Okay. So let us take a neutron. Okay. So in a neutron you have one proton and one up quark and two down quarks, correct. So on an average where would be the positions of these constituent quarks, right. On an average they would sort themselves into a triangle, right. We will see when we study deep inelastic scattering that this is not really the case, but for this back of the envelope calculation you can take the charge configuration to be this. The up quark with 2/3 charge is floating around there, and there are two down quarks, right. So what is the electric dipole moment of this configuration? You have to take the net distance vector among these and multiply the charge and then add them up, correct. So where are the net distance vectors? So I have I have distance vector going in this direction between these two charges and then in this direction between these two charges, right. That means the net distance vector will be in this direction, right, the distance separating opposite charges, right. And what would be the magnitude of that? The magnitude would be roughly the scale of this problem. So how big is a neutron? It is about a femtometer, right. So the net distance vector, let me get rid of this, is about 10 power minus 15 meters, right. Okay. So if I multiply that with the charge I should get about 10 power minus 15 E times m, E times meters, right, E being the electric charge of the electron, correct, the unit electric charge. It turns out this estimate is not that far off. What we actually measure actual measurement, you get about 5 times 10 power minus 16 sorry, this is not an actual measurement. I am so sorry. I am going to go back to this. This is not an actual measurement. This is an actual expectation. Okay. So this is an actual expectation from the standard model. Okay. When you do a quantum field theory calculation of what the EDM should be of a neutron, you get 5 times 10 power minus 16 times E centimeters. Okay. Now I am going to write down the actual measurement. Okay. So the actual experimental measurement is that they have not measured the EDM of a neutron. What they have done instead is to set a bound, an upper bound on what this is, and that upper bound is about billion times or 10 billion times smaller than what is expected. okay, this is just an upper bound, okay, it is not even a measurement. In other words, this is consistent with 0, right. For all practical purposes you could say that the actual electric dipole moment of the neutron is 0, right, and that is the mystery. You expect a number from just simple arguments and then even with quantum field theory, but then what you actually see is something that is consistent with 0, and the upper bound that they could set with the current sensitivity is 10 billion times smaller than the expected number, right. For all practical purposes one could say that there seems to be no CP violation in the strong interactions, although from naive arguments and even from sophisticated arguments you expect there to be a lot of CP violation in the strong sector, okay. So that is the mystery of what is going on in the strong sector, and that mystery is called the strong CP problem, okay. And we will encounter this also in more detail when we come to the quantum field theory aspects of the course. Okay, very good. Now, I had told you that experimentalists had measured that even CP is violated in the weak interactions, right. So, how did they know this? Okay, how would they have known this? What kind of experiment did they actually do? That is what we are going to investigate next, okay. Knowing how they did this is going to teach us a lot of things about particle physics, about quantum states and so on, and this may appear in your assignment also, okay. So, let us begin by considering the K0 meson, okay. What is the K0 meson? We saw the pi meson, rho meson. What is the K0 meson? It is electrically neutral, right. So it is obvious that it is made up of a quark and anti-quark consisting of the having the same magnitude of the electric charge at least, right. Okay. So a K0 is nothing but a D and an S bar, okay. So this is sometimes called a strange pion. Instead of D bar and UU bar, you have DS bar, right. So K0 is this comes under the class of strange mesons. Whenever you have the strange quark sitting in a meson, they are called strange mesons, okay. And K0 is a archetypal strange meson. Since I can write down a K0 state, I can also write down a K0 bar state obviously, right. So what should be a K0 bar state? It is just a D bar S, right. I just apply charge conjugation to the K0 state and I get that, right. Okay. Now if you just look at the left hand side, these two quantum states have the same electric charge, right, and then everything else about them is the same, right. They can have they have the same spin as well, right, and they are both mesons. So there is nothing that really stops them from interchanging into each other, right. In quantum mechanics, when you have two states with the same quantum numbers, they can mix, right, through the Hamiltonian. You might have seen this in quantum mechanics, right. If not, we are going to encounter it now, okay, and this is a very important part of particle physics. We are going to encounter this in many different guises as the course progresses, okay. So I have not really taught you Feynman diagrams, but I am going to draw one anyway so that you can see how this could happen as a process, okay. It should be intuitive, do not worry about it, we will see all the rules later, but I will draw an intuitive diagram here. So I am going to draw the K0 state like this with the D S bar. So imagine time is going from left to right, then I can write D bar S in the final state. So this is a K0, this is a K0 bar, okay. And the rules of quantum mechanics tell you that if something is possible, it could happen with a non-zero probability, right. If something is possible within the allowed laws and symmetries, it could happen. Is there a pathway for K0 to go to K0 bar? It turns out there is. Okay. How? Because you can now exchange say a U quark or maybe a C quark or a top quark, and you can connect to the other one. You can basically spit out a W boson, and again over here also you can have a U quark, C quark or a T quark and spit out another W boson, and at each of these vertices you would conserve electric charge just like Kirchhoff's junction law, and that way you have a pathway to turn this state into this state. Okay. So, you can have a K0 moving around and it suddenly turns into a K0 bar with non-zero probability, can always happen. Okay. So, that might be so, that would just mean that I may not always measure these mesons as K0 and K0 bar, okay, because they have the same quantum number. I can put them on a superposition. I can always write down some superposition, I am not going to normalize it right here, of these states, and what I will be measuring is not a K0 separately on K0 bar separately, depending on the experiment that I am doing, depending on the measurement that I am making, I can measure various combinations of K0 and K0 bar, okay, depending on exactly what eigenstate that I want to measure, the eigenstate of what operator I want to measure. That is what a measurement ultimately means, correct. So, we are going to see many variations of these combinations. That we will do in the next lecture and see how CP violation was found to be a phenomenon, a true phenomenon in nature. Okay. So, I will end here, we will pick this up next week in the next class. Thanks.